ME204, Dependent Motion Analysis of Particles. In statics, we learned about cable and pulley systems. We use cables and pulleys to give us a mechanical advantage. One of the things that we were interested in was how much weight can the motor lift. But now we're interested in finding out how fast the block will move if the motor is spinning at a certain speed. For more complex cable pulley systems, again, we were interested in how heavy of a piano can this truck lift. But now we also want to know how fast can the piano be lifted if the vehicle is traveling at a certain speed. Pulleys give us a mechanical advantage. However, a mechanical advantage always yields a speed and distance disadvantage. We don't get something for nothing. We have to give something up. So when we get a mechanical advantage, we give up speed and distance. Let's do a quick statics review on pulleys. If a person desires to exert only a maximum of 50 pounds at A, how much weight can be lifted? Well, in order to solve this problem, we'll take the pulley at B and draw a free body diagram. Here's our pulley with our weight. There are two ropes coming up from the pulley, each having an equal tension. The tension in the rope is the same as the tension that's being placed on the system at A, so we have 50 pounds in each cable. We want to know what the weight of the block is. Using static equilibrium, we can solve for the maximum weight that we can hold. The sum of the forces in the y direction must be equal to 0 if it's static. So, 2 times T, or the tension in the cable, minus the weight of the block equals 0. Placing 50 in for T, and solving for the weight of the block, we find that the weight of the block is 100 pounds. So if we put 50 pounds of force in at A, then we can lift 100 pounds on the other end at B. What if the person pulls down at a speed of 2 feet per second? How fast will the weight at B rise? Well, there's several steps that we need to take in order to solve this kind of a problem. The first step is to establish a datum. We want to place a datum at a point that doesn't move. So we're going to put a datum right here at the top pulley. The second step is to write an equation for the total length of the cable. Looking at this cable, we've got several pieces and we're going to measure them from the datum. The first piece is SA. The second piece goes up around the pulley. We'll call that C1. We have two pieces here that we're going to measure as SB, and then finally the last piece that goes around the bottom pulley and call that C2. So the total length of our cable, LT, is equal to SA plus C1 plus 2SB plus C2. Now, to relate this to velocities, we need to take the first time derivative in order to get our velocity relationships. Notice that the total length, C1 and C2 are constants. In this process, those lengths never change. So if I take the derivative of those with respect to time, we should get 0. After taking the first time derivative, to get the velocity relationships, we get an equation 0 is equal to VA plus 0 plus 2VB plus 0. The derivative of S with respect to time, or ds dt, equals v from our basic velocity definition. Solving this for the velocity of A, the magnitude of velocity A is equal to twice the magnitude of velocity B. So VB is equal to 1 foot per second. If we wanted to know what the accelerations were, we can take the second time derivative of our length equation to get the acceleration relationships. In this case, the magnitude of the acceleration at A is equal to twice the acceleration at B. Notice that our mechanical advantage was doubled. We had 50 pounds of force pulling at A and were able to lift 100 pounds. However, our distance and velocity disadvantage was half. We pulled down at 2 feet per second and block B rose upward at 1 foot per second. Here's another example. If A is moved at 5 feet per second, how fast is block B moving? We're going to assume that the cord doesn't stretch. Well, the process is very similar. First step is we establish our datums. In this case, we're going to have a couple of datums. We want our datums to be perpendicular to the motion. So we have one datum here that will be the datum for the cable at B and for H1. However, A moves parallel to that datum, so we can't get any measurement from this datum for cable A. So we need to draw in another datum. We'll draw in a datum again at pulley A, but it's perpendicular to the rope at A. Once we have our datums, we can write an equation for the total length of the cable. In this case, we'll have the length of A. We'll have H2, which is a constant length. We'll have H1, which is also constant. And then we have two lengths of B. So our total length equation becomes LT, length total, is equal to SA plus H1 plus H2 plus 2SB. Taking the first time derivative gives us the velocity relationships. In this case, 0 is equal to the velocity at A plus 0. Because H1 and H2 are constants, they become 0 when we take the time derivative, plus 2VB. Solving for VB, the magnitude of VB is equal to 1/2 the velocity at A. Velocity of B is equal to 2.5 feet per second. How much mechanical advantage did we have? We have a speed disadvantage of 1 to 2, or half. So our mechanical advantage is a 2 to 1. Here's another example. Cord A is pulled down with a speed of 8 feet per second. We want to find the speed of block B. Let's go through our steps. First, we're going to establish a datum. Again, we'll place this at a point that doesn't move, right at the top pulley. Second step is to write an equation for the total length of both cables. Notice in this system that we have two cables, and we need to account for both of them. This is the first cable in blue, and here's the second cable. We can establish lengths from the datum. Here's SA, SC, and SB. Using those lengths, we'll establish the total length of the cable. So our first cable, the blue one, is 2SA plus 2SC. There's two lengths here that are associated with SA, and two lengths here that are associated with SC. Notice that we are neglecting what goes around the pulleys, because we know that those are constant and not going to change. So, the length of cable 1 is equal to 2SA plus 2SC. The length of cable 2 is equal to SB, this total length, SB minus SC to get this length here, plus SB, this length. Simplifying, we get 2SB minus SC is equal to the length 2. Our third step is to take the time derivative of both equations. This will give us 0 is equal to 2 velocity of A plus 2 velocity of C. And 0 is equal to 2 velocity of B minus the velocity of C. Solving these simultaneously, we find that the velocity of B is equal to 4 feet per second. How much mechanical advantage is there in this problem? Again, we have a 2 to 1 mechanical advantage and a 1 to 2 speed disadvantage. Velocity of B is 4, velocity of A is 8. Let's look at another one, a little bit more complicated. If the end A of the cable, right here where this hand is moving upwards at a velocity of 14 meters per second, we want to find the speed of block B down here at the bottom. Again, we go through the same steps. Here's a simpler schematic showing what's happening with these pulleys. There's 3 separate cables in this case. There's cable 1, cable 2, and cable 3. We'll place a datum up at the very top, and then we'll write equations for the length of each cable. This length is SA. Notice that this length is not related to any specific length of cable. The cable begins here and continues around to this point, but we still need this measurement in order to get a total length for this part of the cable. SE is to the center of pulley E, SD to the center of pulley D, and SB to the center of pulley B. Now we can write our equations. Looking at the first cable. The length of our first cable is equal to SD, this length, minus SA to give us this portion of the cable, plus SD, our length from the datum, minus SE to give us this portion of the cable. The second cable is equal to SD. Again, for this length, we need SD minus SE to get this length, plus SB, this total length, minus SE to get this length of the cable. For our third cable, we have SE, which gives us this length, plus SB, which gives us this length, plus SB minus SD, which gives us this length. We now take the time derivative of each equation. For cable 1, 0 is equal to the velocity of D minus the velocity of A, plus the velocity of D minus the velocity of E. Cable 2, we take the time derivative to get 0 is equal to the velocity of D minus the velocity of E, plus the velocity of B minus the velocity of E. And for our third cable, we take the time derivative to get 0 is equal to the velocity of E, plus the velocity of B, plus the velocity of B minus the velocity of D. Once we have our three equations, we can solve them simultaneously. Knowing that VA is equal to 14 meters per second, we are left with VD, VE, and VB. So we have three unknowns and three equations, and we can solve them. Solving simultaneously, the velocity of B is equal to 1/7 the velocity of A, velocity of D is equal to 5/7 the velocity of A, and the velocity of E is equal to 3/7 the velocity of A. That would give us a velocity at B of 2 meters per second. The same relationship for velocity applies to distance. If we pull A up 7 inches, D should rise up 5/7 of that distance, E should rise up 3/7 of that distance, and B should rise up 1/7 of that distance. In this case, D rises 5 inches, E rises 3 inches, and B rises 1 inch. What is the mechanical advantage? In this case, it's a 7-to-1 mechanical advantage. If you only wanted to exert 50 pounds of force, how much weight could you lift? Well, knowing that it's a 7-to-1 mechanical advantage, if we apply 50 pounds of force, then we should be able to lift 7 times that, or 350 pounds. Remember, a mechanical advantage of 7 always yields a distance and velocity disadvantage of 1/7. Now let's look at something a little more complicated. We want to find out how fast this piano is moving upward when it's off the ground 10 feet, if the truck is moving at a constant velocity of 10 feet per second. The total length of the cable is 100 feet. We're going to solve this in a similar fashion as we did with the pulleys. The first thing that we need to do is write an equation for the total length of the cable, but in this case it needs to be in terms of x and y. This cable to the truck is not being pulled in a straight line from where it currently is. It's being pulled in the x direction, which means that the angle up here is getting larger and larger. So the relationship is not as direct as it is with a pulley. To write an equation for the length of the cable, we need to look at what the x position and the y position is for our cable. We'll define this distance as y and this distance as x. With those defined, we can write our total length equation. The first portion of our cable, the vertical portion, is simply 50 feet minus y. The angled portion of our length we can find using the Pythagorean theorem. It is the square root of x squared plus 50 squared. Knowing those, we can write an equation for our total length of the cable. We know the total length is 100 feet. So 100 is equal to 50 minus y plus the square root of x squared plus 50 squared. Let's solve for y to make this a little simpler. If we solve for y, y is equal to the square root of x squared plus 50 squared minus 50. Now, as with the pulley problems, we simply want to take the first time derivative. However, time is not a factor in this equation, so we have to use the chain rule and take the derivative of y with respect to time, which means that in our final solution, we're also going to have the derivative of x with respect to time. dy dt is the same as the velocity in the y direction, and dx dt will be the same as the velocity in the x direction. So, taking the first time derivative, using the chain rule, we get dy dt is equal to 1/2 x squared plus 50 squared to the negative 1/2 power times 2x times dx dt. Simplifying this and replacing dy dt and dx dt with velocity in the y and velocity in the x respectively, we get the velocity in the y direction is equal to x times the velocity in the x direction over the square root of x squared plus 50 squared. However, to find the velocity in the y direction, we still need to know what our position is in the x direction. We know what our velocity is in the x direction. That's given to us at 10 feet per second. But we need to find this x position. We'll find that by using this equation and plugging in 10 feet for y. When y equals 10 feet, x equals 33.2 feet. Once we know that, we can solve this equation using x equals 33.2 feet and knowing that the velocity in the x direction is 10 feet per second. Then we obtain a velocity in the y direction of 5.53 feet per second. So, when the piano is 10 feet off the ground, with the truck moving at 10 feet per second, the piano is moving upward at 5.53 feet per second. In summary, when we're solving this type of a problem, there are a few steps that we need to take. First, we establish our datums. Second, we write an equation for the total length of the cable. Third, take the time derivative to get velocity relationships. And fourth, take second time derivative to get the acceleration relationships. Our next topic will be relative motion analysis of particles.